Welcome students, and in this video we are going to continue our study of second order equations, right? So we were looking at a general equation second order, and so it will look like this, right? A times uxx plus b times uxy plus c times uyy plus dux plus euy fu equals to g. So that's your general equation, right? And of course, I mean, g can be 0. That's not a problem. So if you want, you can just put it to be 0 or put it to be g. It does not really matter. Now the point is this. See, we have calculated. So we actually defined something called a discriminant d. And what is, the discriminator? Let's just call it like this, delta. And this is what? This is basically b square minus 4 times AC. So see, this is the problem which is defined in some domain omega, which is subset of R2. This is in 2 dimension, right? Not in 3 dimension, not in 4 dimension, only in 2 dimension. This is true. Now, what are ABCDs? This is given that it is also given that all these A, B, all these coefficients basically are smooth. Smooth means they are at least continuously differentiable. It means that, see, these are functions of x and y. A, B, C, D, E, F. These are all functions of x and y, functions of x and y. Okay, so when I say they are at least C1, smooth means C1. It means that both all the partial derivatives exist. So ax exists, ay exists, bx exists, by exists, and they are going to be continuous. So we are going to assume all that. Right now, you see, essentially this is your discriminant, and is called discriminant. Is called the discriminant and minant. And the point is this. You see, these evaluated at the point x naught y naught will actually tell us the nature of the equation, right? So we we have classified that this is just a name which we gave. So this is the elliptic equation. The equation is elliptic at x naught y naught if this is positive, right? If delta is positive, and it is parabolic if this is 0, parabolic if delta is 0, and it is hyperbolic is elliptic if it delta is negative, hyperbolic if delta is positive. Is it okay? So this we have already looked at, and we have also looked at is this. See, star may be a very it's a general form, it's a complicated form, but the thing is we can actually have a transfer change of variable, and we can reduce the whole problem to a much simpler problem. Of course, the problem which we actually end up with didn't look much simpler, and it actually looked much complicated. So we are going to make that thing more precise, right? So this video, what we're going to do is talk about canonical forms. Canonical form is the most basic form. Think of it like this. So what happens is this. So first of all, we are of course you do realize that, you see, the nature of the problem star depends on the coefficients a, b, and c, right? So we will assume, so this is our first assumption, assumption 1, that a, b, c, they are not 0. A, b, and c are not 0. Okay, this is what we are assuming. So basically they are not simultaneously 0. That's what we mean basically. Yeah. And let's say there is a change of variable. What is the change of variable? Xi and eta. And eta, this is a new variable. Be the new variable. Okay, new variable. And what does this do? Such that a star, c star, a star and c star. What is a star and c star? If you remember, we talked about a star and c star, right? Exactly the same, those a star and c star. Vanish. So basically what I mean by this, if you remember what are a star, b star, if you don't remember, go back to the original video, but the last video. A star is nothing but this: a xi x square plus b xi x xi y plus c xi y square. Okay, and what is c star? C star is exactly the same thing, but in terms of eta. So it is a eta x square plus b eta x eta y plus c eta y square. Clear? Now we want both of these coefficients to be 0. See, the whole point of this is, as I told you, the modified equation, right? The modified equation, if you look at that modified equation, we want to make it in a much simpler way, right? And the xi and eta, this is a new coordinate, so the choice is on us. We are choosing it in such a way that the original equation actually reduces to a much simpler equation. Yes, And you see, these two equations are basically same. If you think about it, 1 and 2. So 1 and 2 are basically same, and it means that xi and eta solves 1 and 2. You see, it means this implies that xi and eta are roots of this equation, right? Roots of this PD. What is the PD? It is A, let's say theta x square plus B theta x theta y plus C theta y square equals to 0, right? What do I mean by this? I mean, if you replace theta with xi and eta, this 1 and 2 is valid. So basically we want to find xi and eta such that 1 and 2 are 0. And if you, and again, and since 1 and 2 are exactly the same looking thing, they are 0, it means that essentially xi and eta are the roots of this particular equation. Is it okay? Now you see this equation, how we can write it. We can just, modify this equation, and we can write it like this. A times theta x by theta y square plus B times theta x by theta y plus C equals to 0. Yes. So basically that equation xi and eta, of course we are assuming that xi eta square. So basically you see, again, the choice of xi and eta is on us, right? Is on us. So we can choose xi or eta in such a way that they are not 0 essentially. We can choose in such a way. So basically here we are saying, what we are doing is we are basically dividing it out by theta y square, divided it out by theta y square, and then we get this. Now you see, if I divide it out by theta y square, this is what I am going to get, right? So along the curve theta equals to 0. Let's see, theta equals to, constant, theta equals to constant. Along the curve theta is to constant. What happens? We have d theta, yes, and that is equals to, if you remember your this thing, the what is it, chain rule, right? It is xi x dx plus xi y dy, right? And that is equals to 0. It's okay. What is, sorry, theta, I wrote it to be theta, right? So it is theta x theta y. Theta is a function of x and y, right? So d theta is d theta del x dx plus del theta del y dy, and that is going to be 0. So basically along this curve theta equals to constant, d theta is going to be 0, right? Because the differential is 0. So that will imply that dy by dx is nothing but minus theta x by theta y. Clear? Now if I replace this dy by dx in our this equation 3, what do we get? So therefore replacing dy by dx in 3, we have a dy by dx square plus b, minus b, no, this is a minus sign is there, so this should be minus b, and then dy by dx plus c equals to 0, right? See, dy dx is minus theta x by theta y, so that is why this minus sign is there. And of course, you see this equation, basically this is a quadratic equation. You can see this is a quadratic equation in dy by dx, and we can solve, right? We can solve this thing. The roots are dy by dx. So dy by dx, the first root is given by b plus root over b square minus 4ac by 2a, right? That's the first root, and the other root which is there is again dy by dx is the corresponding minus, so b minus root over b square minus 4ac by 2a, right? Those are the two roots. Now you see basically what is happening, all of this is true along the curve theta equals to constant, right? Along the curve theta is to constant, these are true, and these two equations, these are called the characteristic equations. Please don't get confused with the characteristic equation of first order. This is different. Characteristic equations, not different, basically the same sort of thing. There, if you remember, we got the characteristic equations along some particular integral curve, right? So essentially what we have is this, This is also similar sort of idea, and but this is of course in a second order setting, not that particular setting. So this is a characteristic equation, we call it like that. And you see in this characteristic, so basically these are the if you look at it, this is nothing but an ODE, right? This is an ODE, right? And in this ODE, so what we wanted to do is to see these are the ODEs for a family of curve, right? For a family of curves. So what does this ODE signify? This ODE signifies a family of curves. And what are, so how do you characterize such a family? In the xy plane, in the xy plane, right? Such that, you see, all of this is true because when theta is constant. So basically what is theta? Theta is nothing but xi and eta. So such that xi is equals to, and xi equals to constant and eta equals to constant. Now maybe I can write it together, and eta equals to constant. So I hope you have understood what I'm trying to say. So essentially what is happening is this, these particular two equations, the characteristic equation, what does it actually model? So basically this actually represents the family of curves, right, in the xy plane, because this is all in xy. This actually represents family of curves in the xy plane. And what is the property of those curves? The curves are such that xi and eta are going to be constants, right? And those curves, the integrals, so basically these integrals are called the characteristic curves. So basically the solutions, so you can think of it like that. Okay, so now you see, the thing is, you can of course solve this, right? So let's call this that is 3, right? So let's call this 4 and let's call this 5. So basically we can solve 4 and 5. So solving 4 and 5, we have phi1 of xy equals to c1, and that's a constant, and phi2 of xy is another constant, c2, right? If you solve it. Okay, now the thing is this, see, if you remember what was our original goal? Our original goal was such that we have to find two change of variable. So what are the transformations? So the transformation is in question. So this is the transformation which we are going to choose. Transformations are given by xi is phi1 of x comma y, and eta is phi2 of x comma y. Is it okay? And so basically what happens is, with these two transformations, so you can change the equation. Which equation? This original equation star into the canonical form. Okay, right? So let's look at some how to do it in different contexts. So basically you see, you do realize we have to solve these two characteristic equation in order to get what phi1 and phi2 was, right? Yeah, whatever the solution you are going to get, we are going to take xi and eta to be those. Yes. Okay, now you do realize, you see, these two equations, the characteristic equation, b square minus 4ac plays a very important term here. Now if b square minus 4ac is positive, if it is 0, if it is negative, depending on that the whole nature changes, because the characteristic equation also changes. Yes, so let's look at all these properties. The first property is this, the hyperbolic case, hyperbolic type. We know that in hyperbolic type what happens? B square minus 4ac is going to be positive. Yes. Okay, so if this is positive, you see here b plus minus root over b square minus 4ac by 2a. B square minus 4ac is positive, so essentially we are looking at a positive term, that's all. Yeah, and so what we have is, we have two real distinct family of characteristics. That will imply that one has two real and distinct family of characteristics. So family of characteristics means whatever you see, the curves which we get solving the characteristic equation, we call those the family of characteristics. Is it okay? Right. So I hope you understand. See, b square minus 4ac is positive. So one I get corresponding to b plus, another I get because of b minus. So two different, two distinct and real. Okay. Now, and of course, if you do that, you see what is happening to our original equation. Yes, in our original equation, you see a star and c star is basically 0. You see, we have chose xi and eta in such a way that A star and C star is basically 0. So we are only going to left out with B star. Yes, and what happens is, so you will be, and the the transformed equation also looks like this, basically A star B star C star replaced by A star B star C star. So you see A star and C star, these two terms won't be there, right? So basically you will left out with B star u of xi eta, right? It will be changed to u of xi eta, so it will look like this. So therefore star reduces to u of xi eta equals to H star by B star. Only B star is remaining, so B star. Yeah, and of course you can easily show that B star is going to be non-zero. Yes, this B star is going to be non-zero. You already know what B star is. Yes, so please show that. So this is something for homework. You just have to check it. B star is non-zero. So all of this is true. And then this is the first canonical form of a hyperbolic. So this is called the first canonical form of a hyperbolic equation. Canonical form of hyperbolic equation. Okay, let me explain to you again what is happening here. We have a equation. Initially this is given to us, this star is given to us. It's a complicated equation. Yeah, and you see, we actually, in the earlier video we saw that we can actually reduce this thing to this transformed equation, right, which is in terms of A star and xi and eta, where A star, B star, C star, all of this is given like this. Yes. Okay, now you see what we did is we actually chose our xi and eta in such a way that A star and C star are 0. So basically we are only left out with this particular term along with the lower order term, but lower order terms does not contribute to the overall behavior of the problem. Of course, I mean the solution problem changes, but the thing is the behavior of the problem, whether it is elliptic, hyperbolic or parabolic, does not change. Yeah, so in this case, for the hyperbolic case, what happens is A star and C star are going to be 0, two distinct you see here we get two real and distinct family of characteristics. Okay, so once you put it down, you can show that B star is not 0. What is B star? B star is this particular term. You see B star. You can show that this is going to be non-zero. Once you show this is non-zero, because you know what xi and eta are, right? Once you solve it, you know what xi and eta are. You can see that B star is non-zero. So the whole problem reduces to something like this. U of xi eta equals to A star by B star, and this is called the first form of canonical form of hyperbolic equation, right? Canonical form is the most fundamental form, the most simple form. You strip it off of all these, in a what I am trying to say is this: you are already given a equation in a particular coordinate, and we are changing the coordinate into a different kind of coordinate in such a way that the equation becomes much easier to solve. That's the point. And of course what happens is, you see, you have xi and eta. Now choose, if you choose, and this also I want you to check. This is very, very important. If you choose xi plus eta to be alpha, there is a new variable. See, initially we have x and y, we change it to xi and eta, and that will give us the first canonical form. Now what you can do is, you can always do another change of variable, which is that alpha is xi plus eta and beta is xi minus eta is beta. You can do that change of variable, and once you do it, you can see that this equation, this actually changes to something like this: u alpha alpha minus u beta beta equals to some lower order term. So some lower order term, lower order term. And what are the terms? Lower order containing which terms? Alpha, beta, u alpha and u beta. Is it okay? So basically first order or zero order, those terms will be there. So the highest order term is only this. Here the highest order term is u of xi beta, but here it looks like this. So this is the second canonical form. Now if you remember the prototype of hyperbolic equation we were studying about, we looked at we told that wave equation is the prototype, right? And the one dimensional wave equation is actually looks like this. One dimension because x is in the space variable one dimension. Of course t is always one dimension, that's a time variable. So utt minus uxx equals to 0. That's your wave equation, right? That's what we told you. And you see, if you look at this and this equation which you got are basically the same equation. Of course, the variable are different, but variable doesn't matter, right? It's just a number. So these two are basically same. So that's the canonical form. Either this first form or the second form. Any two form is fine. Absolutely no issues. Okay, you can use any of the two form. Of course, if you are given to find a particular form, that's a different question. But generally speaking, any of the two form is absolutely fine. Okay, so hyperbolic part is fine. Now, what about the other part? Let's look at the second problem, the parabolic part, parabolic type. Okay, okay. What about the parabolic type? So, parabolic type is this. See, initially for the parabolic problem, so star is parabolic if b square minus 4ac is given to be 0. Right now, you see, then the characteristic what happens if b square minus 4ac is 0, you have dy dx equals to b by a for both the equations. So basically, you only have one variable in this case, right? Yes. How do you find another variable? That's the question. Yes. So see, since b square minus 4ac is 0, a star is going to be 0. Yes, a star is going to be 0. That I am quite sure you understood why a star is going to be 0. Okay, because you can just put it in that x star. Where is x star? One second. Let me just show you. See, a star is a xi x square plus b xi x xi y plus c xi y square. Right. So essentially, what happens is this. You see, there is for that particular problem b square minus, so essentially this is a star, if you remember. Okay, so I will tell you why a star is 0. Let's just look at it. See, if b square minus 4ac is 0, then what happens is those two equation coincides, and then that implies that there exists one real family of characteristics. Family of characteristics. Okay, and what we obtain is this xi equals to constant. Yes, xi equals to constant. That's what we are going to get. See, initially this part also, you see, phi1 and phi2, those are the two solutions which you are getting out of these characteristic equations. Once you solve these characteristic equations, those are the two solutions you are getting, phi1 and phi2, and based on that we are defining what xi and eta is. Yeah. Here what happens is this, if b square minus 4ac is 0, you are only getting exactly one family of characteristics. Is it okay? You are getting only one family of characteristics. So let's say phi1, and phi1 is basically phi1 equals to constant. This we already got, that's the solution, right? So basically xi equals to phi1, and you can assume that is basically one integral. The first integral is xi equals to constant. So if xi equals to constant, of course xi x, xi y, all these terms is going to be 0. So basically a star is 0. And we can find that a star is a xi x square plus, so let me do this part, xi x xi y plus c xi y square. Is it okay? Now, of course, this you can write it like this: a times xi x, root a plus root c times xi y square. Yes, and this is 0. Clear? That's what that equation gives, right? Okay, this is 0. And what happens is from this you can actually, so this, therefore what you have is a star. It follows that a star is given by 2a eta x, xi x eta x plus b xi x eta y plus xi y eta x plus c, 2c, no, 2c xi y eta y. So this is the expression which we are ending up with, and we can actually write it like this: 2 times root a xi x plus root c xi y, and again root a eta x plus root c eta y. This is going to be 0. This is for an arbitrary value of eta x, x y, which is independent of xi. We have to choose it in such a way that it's independent of xi, right? So essentially, if you choose eta to be y, so choosing eta such that it is independent of xi. Okay, if you choose something like this, then the Jacobian does not vanish, so basically it's independent of psi. So now with this, what happens is the original equation, if you look at it, huh, mm, what do you get from this equation? What do you get is this. It becomes u eta eta a star is 0, and similarly you see so the whole problem, what does it happens? Uh, I wrote one second. I made a small mistake here. I should not. You see, B star. This B star is this, right? So that is why it should be B star also. One second. Sorry, I wrote this to be A star. This is B star. Okay, so A star is 0 and B star is going to be, I mean, this is also 0, right? So if A star and B star are basically 0, what you have is only the C star part. So basically the equation, actually, if you divide it out by C star, it becomes u eta eta equals to some lower order terms containing what are the terms? Xi, eta, u xi and u eta. Okay, and C star is non-zero. Is it okay? Yes. So A star is 0. A star is 0 because we chose, see, xi is only given to be constant here, so we can have A star is 0. Okay, now see, again, as I am telling you, the choice of eta is on us. Given xi, we can choose eta in such a way. How do we get xi? We get xi by solving the characteristic equation. Now the thing is, the choice of eta is on us. We can choose eta in such a way that the the Jacobian is not 0. So basically it is independent of psi. Once we do that, we choose it in such a way, it's the most simple part, that the equation becomes much easier. If you choose xi eta equals to y, now you see in that case B star, which is this, it becomes 0. Is it okay? Once that is true, then what happens is we actually have the canonical form parabolic equation, which looks like this. So this is called the canonical form of a parabolic equation. Okay, what I want you to do is this. See, I mean, please, I mean, if you are a little bit confused with the theory part, at least this part, what I am going to do is, after this, after the studying the elliptic equation, I am going to give you an explicit, all the explicit examples of this hyperbolic, elliptic and parabolic types. Okay, so that it becomes much clearer of what is happening here. So now let's look at the third part, the elliptic part, the elliptic type. Okay, so you see, the question is this: we have to find xi and eta, right? Okay, let's look at this problem. What is it? Yes, we have to find, so xi and eta, and to find xi and eta, what are you doing? You are basically, first of all, reducing the characteristic equation, solving the characteristic equation, and then the solution, let's say it is given by phi 1 and phi 2. We are choosing our phi and eta in such a way that so psi is phi 1 and eta is phi 2. This is how we are choosing it. Yes. Okay. Now once that is there, for the elliptic case, if see, b square minus 4ac is negative. Yes. So these particular things, if the solutions exist, they are going to be complex, right? They are going to be complex. Okay. So, and you know that if it has one complex solution, the other one will be the conjugate of it. Yes. Okay. So we have to take that into account, right? So let's say if you somehow get xi and eta, yeah, psi and eta two. So solving the characteristic equation, let's say that xi and eta you have already found. So since xi and eta are complex numbers, are complex, okay, what do? We introduce real variables. So we introduce real variables. See, the whole point is this: we want to find xi and eta in such a way that they are real variable. Is it okay? Now, how do you find something like this? See, I mean, if you solve the equation, if you carry on, think about it this way. This is complex, this is complex. So if you solve the equation, the phi 1 and phi 2 which you are going to get are basically complex. It will involve complex, so real part and imaginary part. So xi and eta, what you are going to get, that will also be complex and imaginary part, both part will be there. But the thing is, we don't want to keep it in a complex variables, we just want to have all real variables. So how do we put it? So since xi and eta are complex, we choose alpha. What is alpha? This we are choosing as xi plus eta by 2, and we will choose beta to be xi minus eta by 2i. Is it okay? So therefore, what is xi? Xi is alpha plus I beta, and eta is alpha minus I beta. Clear? Okay. Of course, xi and eta, because they are complex conjugate, it will be like this, right? And you do realize a and alpha and beta, if you write it like this, they are going to be real. Yes, so they are real variables. Now once they are real variables, then just see that how the equation looks like now. So the equation will look like this, the transformed equation. So the transformed equation will look like this. Transformed equation is a, so maybe I can put double star, because a star is always the transformed equation in terms of alpha beta. Okay, so initially the original equation was given in terms of a, b, c, all this, right? And then xi and eta transformation gave us a star, b star, c star, right? C star. Now in our case, in this elliptic case, xi and eta are complex. So basically what we are doing is we are actually making it in a real variable. So now a star, b star, then again the transformed equation is a double star, b double star, c double star, and this the variable, new variables in this case is alpha and beta. Is it okay? So that's what we are doing. So a double star alpha beta u alpha alpha plus b double star alpha beta u alpha beta plus c double star alpha beta u beta beta equals to some lower order terms containing alpha, beta, u alpha, u beta, and u alpha, beta, u alpha, and u beta. I hope this is clear, right? Now the thing is this, you see, we have xi is this and eta is this. Okay, so what happens is this, a star, so please check this part, check that with these choices, a star equals to c star is equals to 0. Yes, yes. So you can check that part, right? It has to be 0, because it's basically, you see, as long as xi and eta are concerned, it's essentially, I mean, they are complex, but even though they are complex, they exactly mimic the hyperbolic part only. Yes, they are complex, of course, but they actually mimic the whole hyperbolic theory. So basically, a star and c star are essentially in this case will become 0, and the equation then turns this equation, the transform equation becomes a alpha x square plus b alpha x alpha y plus c alpha y square. So this is the first expression, minus a beta x square plus b beta x beta y plus c beta y square, this plus I times 2a alpha x beta x plus b alpha x beta y plus beta x alpha y plus 2c alpha y beta y. This is basically 0, right? And similarly, what happens is you can actually have similar sort of thing, but for one second, I did some mistake somewhere. C times, yes, this is fine. Yeah, the calculation, I think it is okay. Yes, okay. So that will imply what? You see this, I mean, you can easily check that this will imply that a double star minus c double star, okay, plus I b double star is going to be 0, and again a double star minus c double star, okay, minus I b double star is 0, okay, conjugated to each other. And so this actually satisfies that a double star equals to c double star, and b double star is essentially 0. Clear? So as I told you, it's basically the hyperbolic part. If you just think about it, I mean, very much looks like this. Not of course the same thing, but it very much behaves like this. Not like the parabolic thing. Yes. So in this case, what is happening is the first and the third variable A star and C star is going to be is equal, and B star, the middle one, is going to be 0. Yeah. And then the equation transformed into this: A double star U alpha alpha plus A double star, because C double star and A double star are basically same. So U beta beta equals to some lower order term which contains alpha, beta, U alpha, U beta and U. Clear? Okay. Now of course you can divide this whole thing down to with A double star. So that will give you U alpha alpha plus U beta beta equals to, dividing out, it becomes L by A star. So again that will be another lower order term containing all these things, right? So essentially a lower order term, let me write it like this: L star, alpha, beta, U alpha and U beta. Clear? So this is called the canonical form of the elliptic equation, okay, elliptic equation. Yes. So the thing is, this is the theory part. This is how you reduce it. So if you remember, what is an example of elliptic equation we talked about? Laplace of U. How does it look like? Uxx plus uyy equals to 0. This is the Laplace equation, and I told you this is the prototype of a elliptic equation. You see, it exactly looks like this. And what is the lower order term? In this case it is 0. So uxx plus uyy equals to 0. Okay. So this is what basically elliptic, parabolic and hyperbolic equations are nothing but the prototype is essentially Laplace, heat and wave. Okay. And in the next videos, what we are going to do, we are basically going to show you with explicit examples how to reduce these problems to canonical forms. Explicit examples. This is the theory part. And okay, if you are you may be a little confused because it's lots of calculation going on here. Once we do the problems, it will become extremely clear to you what is happening. So with this, I am going to end this video. Thank you so much.